All right, so here we go. This is part 2 of section 3.7. We're solving related rates problems, and we're going to take a look at the guidelines, steps we should go through, the process to make this happen. Okay? Guidelines for solving related rates problems. Identify all given quantities and quantities to be determined. So first step is to figure out, okay, what are we measuring here? What are the variables of the situation? And what do we need to find? And what is our job to solve for? What is the quantity we have to determine? Sometimes drawing a picture and labeling helps, okay? And then somehow use that information from part 1 to write some sort of an equation that involves those variables whose rates of change are either given or are to be determined. So you write some sort of an equation. So this is going to require you to dig into your knowledge base. So there's volume problems and area problems and surface area problems. In general, though, these are mostly going to be things that you should know formulas for, okay? And then step 3, use the chain rule and implicit differentiation to take those derivatives with respect to time. Now, I'm kind of not really happy that the guidelines, and I got this right out of the textbook, say with respect to time, because there is nothing about related rates problems that require time to be the independent variable. It just usually is. But I'm sure that if we spend a little bit of time, no pun intended there, if we spend a little bit of time, we could find a related rates problem somewhere where the independent variable was not time, where we didn't implicitly differentiate with respect to time. It's usually what we do, almost always, but almost always isn't always. And I'm a big stickler. I'm a big fan of not talking in absolutes, because I think talking in absolutes is a bad thing to do, because things aren't absolute. Rarely do we run across things in life that are truly just always one way or another. And then step 4, after completing step 3, substitute into the resulting equation all the known values. So this is after you've taken the derivative, plug in the numbers that you know, the values that you know, and then solve for the required rate of change. Solve for the things you were told that you're going to have to determine. Okay, so how is it again? Read the problem, figure out what your job is. So read the problem, figure what your job is, write an equation, take a derivative, substitute in, solve for the thing you're supposed to solve for. Okay? All right, so here we go. A ladder that is 10 feet long rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? All right, so I read the problem. I think I got a handle on it. I've got a wall over here. So we'll label that. I've got a ladder leaning up against the wall, okay? And that ladder is 10 feet long. That is a constant value because the length of the ladder does not change, okay? Now it tells me that the bottom of the ladder is moving in this direction. And if the bottom of the ladder moves in that direction, the top of the ladder moves in this direction. Okay. It also tells me that the bottom of the ladder slides away from the wall at a rate of change of 1 foot per second. So this is moving in this direction at a rate of 1 foot per second. And then I'm supposed to find out how fast, that is, what is the speed that the top of the ladder is sliding down the wall when the bottom of the ladder is 6 feet from the wall. Okay. All right, so what I'm going to do is I'm going to come in here and I'm going to label some things. I'm a big fan of X's and Y's, but choose whatever letters you would like for this. I'm going to call this horizontal value there X. I'm going to call this vertical value there Y, and that means then that dx dt is that 1 foot per second because it is the rate of change. It is how X is changing. And then when is that happening? Well, that 1 foot per second is when X is equal to 6 feet. Okay? My job is to solve for dy dt. That is to find out how fast the top of the ladder is moving when the bottom of the ladder is moving at 1 foot per second, and it's exactly 6 feet from the wall. All right, so I read the problem, I looked at it all. I think I see an equation there. Now, there is an assumption we're supposed to make. That assumption we're supposed to make is that We live in a world where builders build walls at right angles to floors. And then that would tell me that the equation that I'm looking at here is a simple Pythagorean theorem problem, that x squared plus y squared would be equal to 100, or 10 squared. All right, so I've got my equation right here. I know that x is a function of time. I know that y is also a function of time, because as the bottom of the ladder moves away from the wall, the top of the ladder has no choice but to come down the wall, because the ladder can't change. It's stuck at 10 foot. Okay? So then I'm going to talk about how does this thing change when time changes. That is d dt. Take the derivative of this with respect to time. All right, so I see three terms. X squared is the first term, y squared is the second term, 100 is the third term. I'll take the derivative of the first term with respect to time. The derivative of x squared with respect to t, the variables don't match, so this is the implicit differentiation part. So this is going to be 2x times dx dt. Remember, chain rule says when you have a variable squared with respect to time, with respect to a different variable, in this case x's and t's, derivative of x squared is 2x times derivative of x with respect to t, plus second term y squared is going to be similar. It's going to be 2y times dy dt, and then of course this is going to be equal to 0 because the derivative constant is 0. I just want to highlight something right here. This is a very common mistake at this point. People will take the derivative of 100 and get 100. Remember, the derivative constant with respect to any variable is always going to be 0. Right? All right, at this point, I'm looking at an equation that contains not 1, not 2, not 3, but 4 different variables. If they want me to solve for any of them, in this case, they want me to solve for dy dt. The other 3 must be given. So what's x? Well, I know that. X is 6 feet. What's dx dt? I know that also. That's 1 foot per second. What's y? It never gave me y. Did I miss it in the problem? If I go back to the original problem, ladder 10 foot long, use that. Bottom of the ladder slides away 1 foot, use that. How fast the top sliding when the bottom is 6 feet? No, it never gave me y. So that means one of two things. Either this problem is undoable, or I'm missing something. There must be some way to use the given information to solve for the variable y. There must be some way to use the given information to solve for the variable y. And if I go back to that pink equation, I know that x squared plus y squared is equal to 100. So that means that when x is 6, 6 squared plus y squared is equal to 100. That gives me y squared is equal to 6 squared 36, 100 minus 36. So what is that going to be? 64? Which means that y is equal to, mathematically, plus or minus 8. Realistically, negative 8 makes no sense because it's a length measurement of the height at the top of the ladder at the top of the wall. So negative number doesn't make any sense. So y must be 8. So then I can put that there and say that y is equal to 8 foot. So now I'm going to take all of that over to here to the right, and I'm going to say that 2 times 6 feet times 1 foot per second plus 2 times 8 feet times dy dt is equal to 0. 2 times 6 times 1 is 12, so 12 feet squared per second plus 16 feet times dy dt is equal to 0. Again, I'm solving for dy dt, so I'm going to have to take this, move it to the right-hand side, and then divide by 16. So that's going to give me then that dy dt is equal to negative 12 square feet per second divided by 16 feet, right? Or dy, whoop, I need to save some space to write the final answer, so I got to write this a little bit smaller. or dy dt is equal to negative 12 over 16. They both divide by 4, so that's going to be negative 3/4. Feet squared per second divided by feet is feet per second, or dy dt is equal to negative 3/4 feet per second. I'm just going to stop there. I'm actually going to zoom in on that for a second and say, does that make sense? Because I'm seeing something here. Does a negative number make sense? Well, let's go back to the drawing. Is y getting bigger or is y getting smaller? Because if y is getting bigger, then dy dt would be a positive number. But if y was getting smaller, then dy dt would be a negative number. And it looks to me like since the top of the ladder is sliding down the wall, that measurement y there is getting smaller. And if y is getting smaller, then dy dt, the rate of change of y, needs to be a negative number. And so a negative 3/4 feet per second makes sense to me. So the final step then is to write this up and make it look pretty and make it make sense in terms of the bigger problem. So the top of the ladder is moving down the wall at 3/4 feet per second. Now you might be asking yourself, hey, wait a second, where'd the negative go? That's what we talked about earlier. That's the negative. It's moving down the wall, which tells me it's getting smaller at a rate of 3/4 feet per second. All right, so we're at 12 minutes. I think we can cram another one in this one, and maybe the second one will go a little faster since we got a little more experience. All right, so our second related rates problem. Air is being pumped into a spherical balloon so that its volume increases at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? Volume of a sphere, in case you didn't know it, I'm sure you did, but we'll put it there just in case. Volume is 4/3 pi r cubed. Okay, so here's what I'm seeing, and of course in my world, balloons are red. Then there's the air hose. The air hose will be blue. And air is going into this balloon so that its volume is increasing at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? Oh, they're messing with us here, because normally when you talk about a sphere and the volume of a sphere, you have this sentence. Volume is 4/3 pi times the radius cubed. But they gave us information about the diameter, but they want us to find out information about the radius. So we're going to have to be able to see that. They're trying to trick us there and say, well, if d equals 50 centimeters, then r equals 25 centimeters. Okay, all right, so I've got an equation v. V is a function of time, so that is changing with respect to time. I got a variable r. R is also changing with respect to time. And if both of those are changing with respect to time, then there's not much else to do. We can just start taking derivatives and make this thing happen. All right. So if I differentiate with respect to time, derivative v with respect to t is going to be dv dt. The 4/3 and the pi are just constants, coefficients technically, so they just drag along. Derivative r cubed with respect to t, the variables don't match, so we're going to have to use the chain rule in implicit, is going to be 3r squared times dr dt. At this point in time, I'm seeing 1, 2, 3 variables. And so whatever one they want me to solve for, they better give me enough information or give me the other two. Right. And it looks like they want me to find out how fast the radius is increasing. So they want me to find dr dt, the rate of change of the radius. How fast is the radius increasing? So then the other two must be given in the problem. Now we've already talked about the radius. The radius is 25 centimeters. Okay? But what's dv dt? Well, dv dt is the rate of change of the volume. It's the rate at which the volume is either increasing or decreasing with respect to time. And we were told that air, in this case, is being pumped into the balloon. So volume is getting bigger. So that means that this is actually going to be a positive 100 cubic centimeters per second. Do you see why I'm making a big deal about this thing being a positive 100? Right? Because all we'd have to do is scribble out into and replace it with out of a spherical balloon. Pump the air out. Now that same 100 that's right over here would be a negative quantity. So we need to make sure that we're keeping track of things properly. Air is going into the balloon, so that means that dv dt needs to be a positive quantity. All right, so plugging in everything where it goes, that's going to then give me the equation. What equation is that going to give me? That's going to give me 100 cubic centimeters per second is equal to 4/3 times pi times 3 times 25 centimeters squared times dr dt. Right? Since all of these are being multiplied by dr dt and my job is to solve for dr dt, I'm just going to divide everything by that, and then that will give me that dr dt is 100 cubic centimeters per second divided by, let's see, this 3 is going to cancel that 3. 25 squared is 625 centimeters squared. And then I got to do that times 4. Let's see, what's 4 times 625? Yes, I'm grabbing my calculator even for that. That's 2,500. So divided by 2,500 pi square centimeters. Right? Canceling units and simplifying, that gives me then that dr dt is equal to 1 over 25 pi centimeters per second. Or the radius is increasing. And how do I know it's increasing? Positive number there. At a rate of 1 divided by 25 pi centimeters per second. All right. Related rates. I think I have a couple more examples. Two more examples. That will be in the next video. So would that be part 3, I think? We'll have 2 more examples in it. All right, I'll see you back here for that one.